In this video, we will talk about the ELF format. This will help us to understand how an executable binary is laid out and how the layout is able to be parsed by computers while the computer is executing them. So ELF is short for executable and linkable format. It is a specific format that forms an executable file or a linkable file. You may still remember these two commands. This is what we talked about for compilation in the last week. So if we do gcc-c, we will be able to generate a file with a suffix of O. And if we do file command followed by the .o file, we will be able to check the format of the file. And for the .o file, it is called an ELF 64-bit LSB relocatable. Here, LSB, if you still remember, that means that it is little endian. Also, similarly, if we do file followed by the generated .out file, which is the file generated after linking using LD, we'll be able to see that the file is in the format of ELF 64-bit LSB executable. So the difference between these two files is that the first file is relocatable, which is the file format that before linking. And the second file is called an actual executable, and this is the file that can be executed by Linux operating system. Both files, though, are in the format of ELF. And this is exactly what it means by ELF executable and linkable format. This is a specific format that can be used by linking and executing. Okay, now before we talk about how a program is actually being executed by a computer, let's just take a look at this program by itself. We're going to do this statically. It's like you are reading an article. If you look at an ELF file, which can be either an executable or a relocatable file, usually we'll be able to see four parts: ELF header, program header table, sections, and section header table. For relocatable, program header table is optional, and for executable, section header table is optional. In these four parts, ELF header is the header of the entire ELF file. It will describe the high-level information of the ELF binary. This will also help direct the computer to the rest of the ELF. Similarly, program header table is composed of program headers. Each of the header point to a specific part of the program, which is what we call a segment. And sections are text or data that are organized in different parts. Usually, some of the sections will be grouped as a segment pointed by a program header. And the last, sections header table contains section headers, each of which describe a section. And this is why if you look at the figure on the right, you will be able to see that ELF header points to program header table and section header table. And for program header table, it points to a segment composed of some sections. Then for section header table, it's going to point to each of the sections. For ELF header, as I just mentioned, it contains the general information for the binary file. It also can be considered as the start of the binary. It's not the start of the execution though, but it contains the information that is necessary for a computer to parse and to understand what's going on inside the ELF file so that the computer can execute it later on. There's a lot of information in the ELF header. For example, it contains the information that whether or not the binary is 32-bit or 64-bit. It also has the information of the entry point of the program, which is the start of execution. Also, it contains endianness, which is what we talked before. Also, it has the instruction set architecture. It has the position and the size for program header table and that of section header table. So again, ELF header is the start of the entire ELF so that the computer can parse, understand, and later on execute the binary file. Let's take a look at an example of ELF header. ELF header occurs at the beginning of an ELF binary. Here, what I'm showing is the first 64 bytes of an ELF. Usually, 64 is the length of ELF header for a 64-bit ELF binary. So the left-hand side numbers is the offset of the bytes in the ELF binary. And then the middle and the right parts are the bytes of the actual ELF. An ELF header is usually in a certain format. Those data are localized in a specific offset of the byte. And for computer, all it needs to do is just to extract the information from a particular offset with a particular size so that it will be able to understand the content of an ELF header. To parse an ELF header, we don't normally need to read them byte by byte. We can just use tools such as readelf. And here, what I'm showing on the right is the output of readelf for ELF header. Here, I'm highlighting some important information that we can extract from an ELF header. So ELF header starts with 7F followed by 45, 40C, 46 represents for the letter of ELF. Followed by that is the class of the binary. And here in this case is 64. If the number is 01 instead of 02, it will mean that the ELF is 32-bit. Followed by that is the endianness of the ELF. And here the ELF binary is in little endianness. So the value of it is hex 01. And then if you look at the offset of hex 34, you will be able to find the size of this header. And as I said before, for a 64-bit ELF, the size of this header is usually 64 bytes. ELF header contains the entry point address. For 64-bit ELF binary, the entry point address locates at the offset of hex 18. And in this case, we can see the entry point address is at hex 630. That is the offset of the binary. It also has the information regarding program headers. Different binaries have different sizes of program headers, but they usually start with a 64th byte of the entire binary because for ELF header, for 64-bit, the size of it is usually 64 bytes, and program headers is usually followed right after the ELF header. And then similarly, for section headers, ELF header also records the start and the size of it. Again, the size of section headers is usually different for different binaries. All right, now let's take a look at program header. So program header records the information about each segment, and it instructs the computer to create and process image according to the information listed in the program header. Each program header contains the following information. It has the type of the program header. There's a type for a specific header, and there are offset, virtual address, physical address, file size, memory size, flags, and alignment for each header. And here each record represents a segment. Offset means the number of bytes of the segment in the binary. Virtual address means the offset of this particular segment when it's loaded into the memory. physical address means that when a page is allocated for this particular segment, what is the offset for this specific page? And then file size and the mem size means the size of the specific segment. And flags means the permission of the segment. R means that the segment is read-only. And you may be able to see W or E for the other segments, which means write or execute. Alignment means that this part of the segment, when it is allocated into page, the size of the segment after allocation has to be a multiplication of 8. Program header is optional for relocatables. However, it is necessary for executable because when a program is being executed, a computer has to read the program header to map those segments into a process image. Section header, on the opposite, is optional for execution but is necessary for linkable format because linker needs section header information to put all relocatables together and link those symbols from each of the relocatables. Here I am showing an example of section headers. As you see, the information of section headers is very similar to that of program headers. All right, that's pretty much for the format of ELF, executable and the linkable format. In a summary, an ELF binary is composed by 4 parts: ELF header, program header table, sections representing data and code, and section header table. If the ELF is an ELF relocatable, then program header table is optional. And if the ELF is an ELF executable, then section header table is usually optional. Now let's work on an actual example and see how the ELF and ELF headers and program headers and section headers looks like in a binary. So I'm going to run this example.out. And as you can see, this is an ELF shared object. Now let's start to read the actual binary. It is a file, and we can read it byte by byte. You may have not been trained this, but let's just vim that. So you see, there are all different kind of binary files. It's not really readable. However, what we could do is to convert that to hex. So in each line, the first part is the offset. The second group is the bytes from like hex 0 to hex 10, which means there are 16 bytes. So here represent 16 bytes. And the last part shows the character corresponding to the bytes showing in the middle. Okay, now let's take a look at the ELF header of this binary. And also, I'm going to use read ELF to read the ELF header of this binary. And I'm going to just do a help. And here we can see that we can read the file header using -h option. And let's do it. -h example.out. Here, you are able to see the information of the ELF header of example.out. And let's compare this information with the byte over here. So the first part is the magic part, which starts with 7F, 45, 40C, and 46. And the second part is the class of the binary, which in this case is 64-bit, so it is 02. Followed by that is the endianness, which is 01. And let's continue. Let's take a look at the entry point address, which is 630, hex 630, and it is shown over here. And let me zoom this in a little bit. So as you can see, this is actually different from what has shown over here. And the reason of this is that the entire binary, as it shows in the data class, is little endian. So if we read the ELF header, it also complies with little endianness. And we know that the start address of the entry point should be in the header, starting with hex 18 and the end with hex 1F. So this part is the function entry point. And again, we need to read it as little endianness format. The first byte is hex 30, the second byte is 06, and the rest of the bytes are zeros. So putting all this together, let's convert that to an integer. And to be more specific, let's convert that to an x86 64 address. So we should read it from the last byte to the first byte. So it should be 0000, again, some zeros, and then 0630. And that's why the entry point address is actually hex 630. Okay, and then let's continue. We will be able to find the start of program headers, the start of section headers, and they are right next to the entry address. And here again, because this is little endianness, we need to read it from right to the left. So the most significant byte is hex 1A, and then the least significant byte is hex 18. And that comes to 6,680. All right, so as you see, this is the entire header, and it does start with the first byte of the binary. So for a computer, it will just like read the first 64 bytes, and it will be able to extract all the information as such. So from this information, we know that the start of program header is at the position of 64. And let's take a look at the header starting from hex 40, which is 64. And also, readelf supports the functionality of reading program header. If we scroll up, we'll be able to see the help message, and program headers can be shown using Option-L. And let's take a look at it. Okay, so for program header tables, it will tell you that there are 9 program headers, and then starting at offset 64, which comes from, again, the ELF header. And then we will be able to see all the information from program header table, which starts at hex 40. For the first record, the type of the header is PHDR, which means this is program header. And this type is represented by 6. And followed by that is flag information. In here, the flag is read, so the value flag is 4. And after that, it is the actual offset, which is corresponding to this part. And then the next is the virtual address, which is corresponding to this part. And then is the physical address, which is the next. And the next is the size, file size, and memory size. And in the end is the alignment 8, which is showing over here. So this is the chunk of bytes that denotes a header of a segment. and there are 9 records as such, and we can know where the program header tables end by looking at the ELF header again. So here we see that the size of program header is 56 bytes, and the number of program headers is 9. So what we need to do is to have 64, which is the start of header, program header, plus 56 times 9. That is equal to 568, which corresponds to hex 238. So it ends at hex 238, which is here. Starting from here, this should be something else. And recall from our diagram that after the program header table is the sections. To read those sections, let's take a look at section header tables. And section header tables can be read with option dash capitalized as. According to ELF header, the start of section headers is at byte 6680, and let's convert that to hex. Which is 1818. Okay, so here is the start of section header table. And similarly, we can see all those bytes that represents the information for the section headers. I'm not going to look into the details and introduce each byte for you for each record, but what I'm going to show you is that for each of the section, the offset represents to the actual bytes of the sections. For example, for .text section, usually is used for the code. We see that the offset is 630, right? So if we go to hex 630, we'll be able to see the codes over there. And in fact, hex 630, as I mentioned in the ELF header, is the entry point of the program. Now you may wonder that how a computer knows the mapping between sections and the segment. And also, you may already notice that there is specific information showing over here if we do read ELF-L, to read the program headers. This information is not actually showing in any part of the binary. However, computer can deduce this information by looking at program headers and section headers. Because program headers has the information of each segment start address and the size, and section headers has the information of each section's start address and size. In this way, a computer will be able to infer which segment includes which sections. And this is also how read ELF works in order to show this piece of information.